Apologies,
No.
but here I am. Here I am. I got
Welcome back.
confused. Sorry. Thank you very much. And I have gone over the questions that you sent.
Right.
Thank you.
Some of them may be repetitions, or some of them you might have covered, but it might be a good idea to go over them.
Of course, of course. Let me do maybe as we did last time, that I start with the written questions and then I move on to live questions. I'm looking at the chat. Sorry,
just one second. I think Adrish wanted to record the meeting.
Oh, of course, of course. So I'm just trying to...
Please go ahead.
By the way, I see that there are things in the chat, but it says 4 things in the chat, but I can't see them. Oh, okay. All right. Let's see. Okay. Madhu Sudananan. Oh, okay, great. So let me first take the ones that are written, and then Madhu Sudananan, I will get to your questions. So thank you all for watching the lectures and asking all these great questions that show that you really watched the lectures. It's really insightful and very good questions. Thank you for asking them. So I'm going to read them out and then I'm going to respond. So the first one is, since guessing noise sequences to guess a sent signal sounds like a fairly simple idea, why is there no previous research on the grand scheme? Who knows? You tell me. Moreover, has any research been done previously on such schemes to guess the noise sequences? We couldn't find any. There has been, research in looking at things like ordered statistics decoding, but that's taking the noise sequence, reworking the codebook, so sort of making a new codebook modified to take into account the a posteriori probability, but it's still codebook based. So you sort of rearrange the codebook with the OSD. So it's still, you style the code starting from the codebook. I mentioned in my lecture on SGRAND, some work that looks at these 2 to the n minus k, but again, it's actually still codebook based. So no, I haven't seen it. And why haven't people done it? Who knows? I think, it's really easy to just take one direction and run in that direction and never stop and look back and go, wait, why am I doing this? Okay. Second question, how does GRAND perform against polar codes? I believe I have shown you those results. And also this can be extended to non-binary channels. The answer is absolutely. So I think I showed you not just BPSK, but some of the results I showed you were QAM. And we are actually doing work right now on higher order modulation. And it actually, the higher the modulation order, particularly high SNRs, the better the performance. You can get a huge amount from that. So it actually can be extended and does particularly well. I just didn't show it in that particular, in this introductory course. Number 3, what information is captured by Renyi's entropies, which is now captured by Shannon's entropy? What is the physical interpretation of Renyi's entropy, e.g. Shannon's entropy is a measure of information? There's a lower bound on the number of bits represent a source. If Renyi's entropy is a generalization of Shannon's entropy, why most of the books and courses on information theory only talk about Shannon's entropy? Okay, so I haven't written a book. We're thinking about it, but I haven't done it, so I can't tell you why other people haven't done it. I can try to give an interpretation of Renyi entropy. So remember, for instance, when we were looking at the Renyi entropy of order 1/2, that basically it was looking, it was sort of more it was a bit more concerned with the tail, right? So that alpha that you're changing in the in the moment, think of it that you might weight more certain unlikely events, or you could change the alpha to weight more really likely events. What's happening with Shannon entropy is you're weighting all probabilities the same. Okay, so rather than thinking even of it as measure of information, that's not really the physical meaning of the entropy. It just so happens that it maps to that, but just as a statistic, without worrying about exactly what properties of that statistic you can show later. When you have the alpha equal to 1, which of course you have to be careful. Like I said, it's a limit because you have that 1 over 1 minus alpha. You can't let the alpha actually be 1. You can only take the limit as alpha goes to 1. What you're really doing there is you're sort of weighting less likely and more likely all the same. As you vary the alpha, you can decide whether you're more worried about some, more unlikely events or whether you're worried about more likely events. So that's the interpretation that I would like to have. The next question, question 3, is a question 4. What is the minimum value of n? If it varies from n0 to infinity, what about the effects of the Rényi entropy rate? I'm not quite sure what you mean by the minimum value of n. Those were limiting results. So if there's no minimum value. If I substitute n equals 0 or alpha equal infinity value of h alpha 0, these cases are applicable for entropies of noise and moments of guesswork. Are the above scenarios applicable for fading channels? How can I achieve a region of convergence to achieve capacity? Kindly explain. I'm going to be honest, I don't quite get this question. So those that we're showing were limiting results, and then I showed you practical results in the small n regime. But limits don't hold. I mean, you can't take the limiting result and just assume it holds for shorter n. Are the above scenario applicable for fading channels? So you could consider different. It depends also how you're modeling these fading channels. I think I showed some results in my very last lecture on channels with memories, so Markov channels. So you can model those Markov channels, and actually, if you look at the original paper on Grant, it does cover a lot of different cases. So I would urge you to look at that paper for channels with memory, which I think is what you mean by fading channels. So you can there are definitely ways of extending it. Question 5, what are success exponents? Not clear. Okay, this is great. So success exponents, which I mentioned in the lecture, but I didn't give you results on, are probability of being correct with Grant, even though you're transmitting above capacity. So as I mentioned in the lecture, usually in information theory, if you're above capacity, people go, oh no, disaster. But actually, even if you're transmitting above capacity for a little bit, and this may actually have a relation to the previous question on fading channels. If you have a fading channel, sometimes for a period of time, your capacity of your channel may actually go below the rate at which you're transmitting. However, if you're guessing and you guess very quickly, even if the channel is on average worse for this period of time that you're transmitting in this fading event is worse than what you were expecting given the rate that you picked, if you guess quickly, the probability that you were correct is still very high. So the success exponents, which have not been looked at until Grant, as far as we know, are the probability that you're able to guess the noise effect correctly and therefore decode correctly, even though you're transmitting above capacity. And so as long as your rate is between capacity and another rate, which I called R prime, I believe in my lecture, and I didn't detail, but again, if you're interested in this, I urge you to look at the original Grant paper from IT Transactions. Then you will see that you can use the fact that you guessed correctly to know that it's highly likely that even though you're above capacity, you have a correct decoding. So that's what the success exponents provide. So that's a good question. Question 6, you showed that the typical set is very quickly guessed. Do you have any performance latency trade-offs of ML versus typical set decoding? So if you're talking about typical set decoding, the way you may have learned it, say, in your information theory class, which is typical set based on the code book, if you go to our second lecture, I actually showed you some graphs. Maybe it wasn't clear in the context that that's what those graphs were showing. In particular, when you recall that we had, the number of guesses, and we had that steep curve that was going up. That was basic, and then we had a flat curve, which was guessing with noise, and then guessing with noise actually became easier as the rate went up. It stayed constant, and then when the rate was sufficiently high, it actually, the complexity went down. But as the rate went up, the other one was going up. That would be actually looking in the typical set of the code from a codebook perspective. So I probably didn't make that connection well enough. So it's a good question. So as you can see, if you were codebook centric, your complexity would be very, very bad, unless your rate was extremely low. So I urge you to look back at those pictures again. Go back to the original grant paper. It does discuss that. Moving along to the next question. 7. How does decoding in the dual domain works? I don't know what you mean by the dual domain. I presume you mean on the noise. Well, I mean, it's just as I said. So I'm not quite sure what that question is. If whoever asked the question wants to clarify in the chat, I can try to take another stab at it, but I don't quite get it. 8. Most of the results you have shown are for short block lengths. How is the performance of code word lengths in the order of tens of thousands? So if you look at the last lecture that I presented, I did present for even with soft information with lengths to the thousands. So they're not necessarily short. Again, I don't want you to think of length of the code. I want you to think of number of redundancy bits. So it's low to moderate redundancy. How is the performance of code word lengths in the order of tens of thousands? So we're extending it now to longer code lengths. I can tell you that we have very good results, but they're not ready for presentation. I would like to sort of step back a little bit, though, and go back to that slide I showed you when we were talking about, right now the tail wagging the dog. That's to say the math making the engineering work a particular way. Why are we using these LDPCs with tens of thousands? If you ask somebody, they say, well, they're capacity achieving. But remember, we're using them at rates which are way below capacity, right? We have bit error rates on the channel that are 10 to minus 3, 10 to minus 4, which means the capacity is 0.99, 0.999. And we're using LDPCs that go from 0.2 to 0.9. So we're using ludicrously long codes to get to rates that if we were decoding correctly, i.e. using GRAND, which is a maximum likelihood decoder, we wouldn't have to use these really low rate codes. So the answer is we are extending it to longer codes, but you really shouldn't. Don't use long codes if you don't have to. If I can get with a short code a rate of 0.95, a rate that's higher than the LDPCs that are being currently used in the 5G new radio standard, why? Why are you using these really long codes? I mean, there has to be a reason. So unless, they could be reasons in certain applications, but unless you have a really good reason, don't use long length codes. They cause more delay. And actually, we have some work showing that they energy very bad in terms of energy efficiency. We haven't published these results yet, but yeah, they're really, really bad in terms of energy efficiency. So you shouldn't use long codes unless there's a really specific reason to do so. Certainly in 5G, from what I've seen, it shouldn't be. Going on to the next
question.
Oh yes, Adrish. Yes, of course.
Follow-up question. So in your you can actually make this heap, right? So even if the code word length is long, you can actually do a parallel decoding. So this should not be a problem for Grant, right? Because you can actually parallelize the whole thing, because you are just creating heap of these noise possible noise vectors, correct?
That's a really good question. That's a really good question. So we haven't looked at parallelizing SGRANT. As I mentioned, SGRANT's a bit more theoretical. It does provide you that lower bound. And as I mentioned in my lecture, I think at this point, now that we're able to give the true minute maximum likelihood, even if you decide not to do it for whatever reason, at least, intellectually, there's no good reason not to find out how far off a scheme is from the actual optimum, right? So I would expect, and I've seen that actually at the last ICASP, that people already have implemented SGRANT even just to compare their own schemes to the optimum. Now, to what extent can we do SGRANT in parallel? I'm not quite sure. I think you seem to have some great ideas, Adrish. What we have been looking in terms of implementing that is Ken Duffy's work on OrbGrant, which I did not describe. Again, this was an introductory course. I couldn't go over everything, but certainly I provided the references. And that's a very stats type of approximation, and it's much, much simpler. And it does basically as well as SGRANT, as you could tell from the curves that I presented. But if anybody has a good idea for how to make SGRANT implementable, I think you seem to have some great ideas, Adrish. Absolutely, I'd be really interested in hearing about them. But I think right now, just as a performance metric, it's also helpful, I think, to understand the theory. I couldn't go too much into the application and the development. But I think that's a good question. What are the hot topics that can be explored in coding theory right now? So let me actually leave that because that's the open problems part of our discussion. Before going to that, I'd like to finish answering all the questions. I have a question in the chat from Madhu Sudananan. From the lecture, the complexity plays an important role. It is a function of noise, but not code rate. How can I correlate with code length along with OAM, QM, using polar codes in order to improve capacity? And then what's the maximum code length I can use to achieve capacity as well as coverage using polar codes? Thank you, Muriel. Yeah. So I think that if you look at the last lecture that I gave, that range there of good rates that I showed you, where you saw, it's basically, again, think of it as how much redundancy you have rather than rate or length. It's actually the amount of redundancy. So it takes some getting used to. It's a different frame of mind. Now, of course, if you have the rate and you have the length, you can, of course, compute the redundancy, but think in terms of redundancy. But we gave that graphic there to give you some idea, if you really wish to think in terms of rate and length, which rate and lengths would be appropriate, and definitely, high rate, and again, in terms of achieving capacity, you with any finite length, you're not going to achieve capacity, but you basically get within spitting distance of it. But I showed you that rate. I showed you that rate length curve, which is really fixing the redundancy to a manageable redundancy. But just as a rule of thumb, I would say 20 bits is very manageable of redundancy. Very, very manageable. You get a lot of tricks. You can combine with SRGRANT. So you could even increase that different ways, but very, very manageable. Okay, let's see if I have. I think I may have another question on the chat. Oh no, that's just a dish. Okay, so let me then go to the other part, which is people asking, what are hot topics that can be explored in coding theory right now? So before I answer that, I just want to make a shameless plug because we currently have a postdoc opening for grant. Actually, there's two of them, one in my group We'll be working together with Professor Ken Duffy at the Hamilton Institute, the co-inventor of GRAND, and also Professor Rabia Zizichijil, who's at Boston University, who's on the circuit side. So there's one in my group. There's one if you're more a circuits person in Rabia's group. So if you're a graduating student in comms, information theory, or maybe more the circuit side, but with an interest in comms and signal processing, which would be presumably why you showed up to this class, then you can look on LinkedIn. I have posted it. I've also posted it on the Information Theory Society website. So please do look at those openings and get back to me. So if you're interested in this topic, just plug for the postdoc if you're finishing up, or if you have friends that are finishing up. What are some of the interesting questions? I think there's tons of interesting questions. Actually, Adrish just brought up a whole vein of possibilities, which I think, how do you implement this in efficient manners? How do you parallelize? How do you really account for the complexity? Maybe going back to the question of what are the hot topics that are being explored in coding theory right now. I mean, to some extent, certainly from the error correcting point of view, it looks like the code doesn't matter that much. Oh, I have another question in the Q&A. Do I need to worry of the existence of alpha moments of GN for lambda sub n alpha? Yes. So the technical conditions for that to exist are actually very mild, and you can find those technical conditions in the original GRAND paper. But in general, you wouldn't really have to worry about that very much. There's some mild continuity conditions. So yeah, in terms of the coding theory, I mean, maybe really what it says is you don't need to worry that much about the code. It's more about the decoder. Certainly, I'd be interested in seeing how well does GRAND do with different kind of noise statistics, how you can take into account the noise statistics. I gave you a little bit of a hint there at the very end of the class when we went over Markov order. But I would really, I'd love to see, this gets back actually to one of the questions that mentioned fading, how you can use knowledge of the fading statistics to improve performance. We always think of the non-uniformity of noise as being a problem that we deal with by interleaving or masking, in a way, the fact that there is correlation. But I would really love to see how we can use the correlation actively rather than fighting it. To me, that's one of the biggest problems. And then that can take many different guises, whether it's looking at capacity results using this kind of decoding. I don't know whether there are codes that you can construct or not. So far, pretty much, again, it's the noise. It's not really the code. So I think there's really interesting stuff to be done there. I think there's a lot of interesting aspects, and this is a school on both information theory and signal processing. I think there's really interesting stuff to be done there at the intersection of signal processing and comms and information theory, particularly seeing how do you acquire the signals, knowing that you're going to be using GRAND on them. I promised that I would show you, and then I forgot to show you, so my fault, some results on how GRAND does with different levels of very simple quantization of the received signal. And actually, this connects a bit to the question people had about the CA polar codes. We found that with very little quantization and GRAND, we were doing better than with current chips that have, quantization maybe 3 to 5 bits, and then applying CRC-aided list source decoding, list decoding with successive cancellation. So, it looks like we can maybe save ourselves quite a bit of bits in the chip by being more, by using GRAND, even by using no smarts at all, in the quantization and the sampling, but maybe there's more interesting things one can do. I think those are very interesting questions. So with that, I'll open it if there's any final questions, and then I will skedaddle. Are there any final questions?
It looks like we don't have any other questions.
Oh, there's one more question from Japnit. Is grant the first work for codes with some guarantees for rate greater than capacity other than outage probability? I haven't seen any, certainly not in a general sense that would work with, any codes, but if you know of any, by all means, email me with that information.
Okay. So thank you very much, Muriel, for taking the time
Thank
to record
you very
the lecture
much.
and for joining us and answering all the questions. Thank you very much.
Thank you. Thank you for the invitation. Thanks everybody also for participating and sending me good, really good questions. It's always nice to have that sort of intelligent exchange. So I appreciate it.
It was absolutely a pleasure to have you here, Muriel. Thanks for accepting our invitation, and thanks for the Padavani lecture. Really, it was very useful. And everybody enjoyed your lectures. Thank you so much.
Thank you very much, and happy to get feedback from people. If there's things you think I could, explain better. It's my first time doing a full short course on it, so I'm sure there were many problems with this the beta version. So I appreciate you being patient. Okay, thanks everyone.